All right. Well, it's my pleasure to introduce our today's speaker, Luz Roncal, and you, please.
Yeah, thank you. Thank you, Sergey. I would like to thank the organizers for the invitation and the chance to be here. It's an honor to be here in Cambridge, to be speaking, and congratulations for the program. It's really nice. So today I'm going to speak about the harmonic type inequalities. For the Dunkl harmonic oscillator. So this is joint work with Professors Ciaurri from Universidad de La Rioja in Spain and Thangavelu from Indian Institute of Science. And actually, I think it's adequate to speak about hard inequalities here in Cambridge. So just to begin with, I'm planning to divide my talk into 3 parts. So I will briefly introduce hard inequalities and some state of the matter. And then the central part of my talk will be about Hardy type inequalities consummation Laguerre differential operator. And then I will conclude by connecting with Dunkl harmonic oscillators. Everything will be more explained. Okay? So the classical Hardy inequality, or one statement of the Hardy inequality in the continuous case and in one dimension, Basque, of course, Hardy. So there are several papers in 2090, 2095, and of course is the book by Hardy, Little book, and Polya. So if you have a function measurable, non-negative in C infinity, and for t bigger than 1, so we say that this operator, that is the Hardy operator, is bounded with the constant by the function. Okay, whatever both sides of the inequality is fine. So if we just rename this quantity like capital Fx, a way to rewrite the Hardy inequality is nothing but this form here. And then you have here the derivative. So you are controlling the function with a way with the derivative. Okay. So if we go to higher dimensions, and in the case p equal 2. Okay, so in this case, it is known that Hardy inequality takes this form. And then here you have the gradient. Okay, so this constant is known to be sharp. Okay, and again, the equality is never achieved in the space of function for which both sides are finite. Okay, well, I could try to motivate these studies. Hardy inequality is very important in many places. For instance, when you have to decide about existence or non-existence of solution of certain partial differential equations, that actually was our main motivation when we began to study these kind of things. But there are many places in which these inequalities are essential. So I would like to notice that there is a fractional version of the Hardy inequality. take a parameter between 0 and the half, the fractional version says something like and then in the right hand side you have to understand this in the product of L2. Okay, so you have to put here the Laplacian, the fractional power, and this in L2. Okay, whatever this means. This is the so-called fractional Laplacian. This can be stated in a spectral way, okay, with the Fourier multiplier. So again, I think that I put the correct sign. No, I didn't put it. So again, this constant is known to be sharp. Okay, this goes back to works by maybe the first one is Hertz in the 70s, Wegener, and Lafay. Okay, independently they prove this kind of inequality. Okay, so in this line, I would like to mention relatively recent paper or work by Rupert Frank, Elliot Lieb, and Robert Seiringer in 2008, in which they improved that inequality in the sense that they give information, quantitative information, about the error made when you take the difference between these two quantities. Okay? So actually, or roughly speaking, the strategy that they follow is a two-step strategy. So first, what they have is to get an integral representation for this quantity, okay, and this deals heavily in the integral representation for this. And once you have that at hand, they define a suitably non-local version of a ground state representation. So there are physical meaning here, and essentially, this ground state representation is a quantity, okay, that is, this is what I will call ZDS, okay, and then okay, and then what they prove is that there is an integral representation for this. That is a positive quantity, not negative quantity. So that, of course, then you deduce the hard inequality, and then you can give the information on this error. Okay. Okay. So with this work in mind, actually, with Professor Thangavelu, we try to look at Hardy type inequalities in the Heisenberg group. That was like something that it was not studied before. And actually, from the things that we learned there, and so because of that, and also inspired by a paper of Gorbachev, Ivanov, and Sergei. Okay, things published this year, in which they consider what is called pitch inequality for the Dunkl transform. So we decided to check the consistency of the method and the things that we learned from it before to the Dunkl harmonic oscillator. And later I will briefly introduce the Dunkl setting, just maybe at the end of the talk. Okay. So that was our idea, that was our motivation, and then we started to study this, and then at some point, we quickly realized that in order to study this, we had to reduce to some setting in which the Laguerre functions are playing an important role. Okay, so this will be the second part. That is Hardy type inequalities for Laguerre operator. Okay, so I will introduce some notation, some basic ingredients. So we have a parameter taken bigger than -1/2, and then what I call the Laguerre operator is a second order differential operator. Okay, and then we are taking R in the half line. That's all. Okay, so it is known that what I will call Laguerre functions form an orthonormal basis in L2 with a measure that I will denote like that, and this measure is nothing like this part. Okay? So this means that if I take a function f, this can be in this space can be expressed like the sum of certain convolution with Laguerre functions. Okay? So this is like a sort of generalization of what is happening in the Fourier setting. Okay? So here this is called the Laguerre convolution. So actually what you have to do here is to you have the integral with certain translation, or that I will call the Laguerre translation. Okay? That generalize, in some sense, the Euclidean translation. Okay? And this Laguerre translation has a complicated that I hope not to cheat quite a lot. Yeah, that is the, sorry. And that is the Bessel function of, I could just jump. Whatever. Okay, so this is our basic setting, and actually we like to since I told you we want to take Hardy type inequalities for this Hardy operator for this Laguerre operator. That means that now I'm thinking instead of the Euclidean Laplacian about this operator. So following the program of Frank Seiringer, I will need an integral representation for this object. And in order to get an integral representation for this object, I would like to know first how this looks in this case. Okay? I need to define the fractional powers of this object. Okay, so the idea first the idea is to use the spectral theory in the same way as it is done in the Euclidean case. Okay? So now So what's happening? There is something that I didn't say that is very important. The Laguerre functions are eigenfunctions of the Laguerre operator, okay? In this way, okay? So if I want to first naively define the fractional powers of this operator, then, for instance, for S between 0 and 1, I could just write something like the eigenvalues to the power S, and then the projection set. Okay, so actually this is the thing that one can expect to define this kind of fractional powers. But actually, we understood and we learned from our previous works that in this case, this is not the suitable way to define the fractional power of this operator. Okay, there are some reasons behind. This Laguerre operator is connected to the sublaplacian in the Heisenberg group. Okay, actually, when you take the sublaplacian into acting on functions that are radial in the first variable, you are reduced to deal with this operator. And actually, when you have to define fractional powers of the sublaplacian in the Heisenberg group, the most suitable thing is not, or the most suitable way is not this one, but with eigenvalues that are quotients of gamma functions. And this has to do with something quite deep that is called conformally invariant fractional powers of operators. Okay, with meaning and roots in differential geometry, scattering theory, and all these kind of things. So the second definition that I'm going to use, and this is the most suitable in this case, I will denote by L alpha S, will be in this way. And then the projection. Okay, this is the gamma function. Actually, when you take alpha big enough, this behaves like that. Okay? Well, so you can believe me, this is the most suitable way to do it in this way because of this geometrical reason. And actually, there are more analytical reasons. For instance, is that this operator, defined like that, has a fundamental solution. And for instance, in this case, we don't know if there is any. In practical thing, that means that also this makes you life easier to compute things. Okay? So this is the operator spectrally defined that we will deal with. But as you remember from the Frank-Lieb-Seiringer, we will need an integral representation for this. Okay? So how are we going to do this? So we will do in the following way. We will take a numerical identity for the quotient of gamma functions. Okay? This numerical identity, let's have it here. Okay, so this is a positive number for us. This can be expressed in terms of certain constant depending on S, plus another constant depending on S, and then what you have here is 1 minus A minus mu T dt hyperbolic sine of this. So why I'm doing this? Okay, because if I use now functional calculus, that means that if I can, and this can be justified in which instead of taking here a number, I can put an operator. this means that here, this represents the heat operator related to this, the operator that I put here. Okay? So, if I think of the case of Laguerre operator, that is the case that I'm dealing with, I can define the heat related to alpha, okay, alpha. I will denote it like this. And again, spectrally, this is defined like n minus t and then the eigenvalues. Okay? So actually, this, for good enough functions, this is the solution of the heat equation with the Laguerre operator with this initial data. Okay? So good news for us, because actually this has an explicit expression in terms of, this can be expressed like a convolution with a kernel, and this kernel is explicit. Okay, this is the former works of Thangavelu. Okay, so now if we come back to this numerical identity and we take mu equal precisely the eigenvalues and then multiply by projections and sum. Okay, what we have is that this equal this, and then equal this with all the stuff. Okay, so we have then something that is CSFR plus, and then I will put here exactly okay. So now the trick is this is representing this. Okay, take the eigenvalues, multiply and sum. So you have precisely this. Okay. So then add and subtract this quantity. And then with a function, okay, add and subtract this, and then put together this minus this, you will have another, I will call it SR, another function that is bounded times our function, and then plus, I'm putting, sorry. Okay, so what you will end up will be with something that is 0 infinity, and then you will have the translated heat kernel times FR minus, okay, and then the measure and dt. Okay, so here, make Fubini, of course you have to justify that this can be done. So so application of Fubini, you will end up with something, of course there is a constant here, minus fu, and then you will end up with a kernel that is this thing together with this, okay? There is no explicit expression, but we know that this is positive and symmetric. That is more than enough for our purposes. So we call it alpha u, and then the extra thing here. Okay, so we call that was the integral representation for our what I call conformally invariant fractional powers. I will just call them fractional powers, okay, to solve. So actually this can be taken like a theorem, and as I told you, the most important thing here is that this kernel and fs are positive, and this is symmetric. Okay, so we have the integral representation. With this integral representation is quite easy, okay, to get an integral representation for L alpha S F F, okay, in the L2, in this case an infinity in our measure. Okay, so this can be done very easily. I will just skip. So first step is done. And then the second one was to define a proper ground state representation and then to see that this is positive. So we will deduce the Hard inequality as a consequence. Okay? So the second step, the ground state representation. So my ground state representation here will be the difference between that quantity and then something that is not an ansatz. Actually, one has to work to predict which will be the left-hand side of your Hard inequality, okay? And then you have to prove it. Okay, so this is the, I don't remember the constant. Yeah, here. This is delta, I will explain it in a moment. And then what you have here, and then you have here some weights that actually is a way depending on some delta. Delta is a positive parameter, alpha and s, and here you have W minus s. So these weights are given in terms of McDonald functions. So McDonald functions are from the family of Bessel functions, and actually they are very nice because they are decreasing, actually decrease exponentially, and they are positive. Okay? So this is our ground state representation, and this will be the left-hand side of our Hardy type inequality for Laguerre operator, for the fractional Laguerre operator. Okay? Why can reach this expression? Okay, actually, if you go and you try to understand the method of Frank-Lieb-Seiringer, this method that lies on physical interpretation is giving you a hint that which will be these weights that you have to put here, because this is strongly related to the fundamental solution of the operator and the action of your fractional powers on such weights. Okay? We are getting an extra parameter, and this will give us, if we try to simplify our Hard inequality in a better way, we will lead to a non-homogeneous way. I will show you in a moment, okay? And we don't know how to get a pure hard inequality with a homogeneous way. But still, this is not possible. But this happened also in the Heisenberg group, actually. Okay? So, okay. I don't know if maybe I will spend some time on this. So, this is our ground state representation, and what I will prove is that this quantity is non-negative. Okay? So, the idea, and this is, the idea is standard from Frank, Lieb and Seiringer. Okay? There is technical work behind, but the idea is from them. And actually, what you have to do is first to polarize the quantity, this quantity, okay? So, you have to take F and G good enough, and I will choose especially this later, and then I will write, no, with the integral representation that I have, that actually is nothing but 0 infinity, 0 infinity. And then the kernel. There are constants that sometimes I'm forgetting. Okay? So you polarize this, and then you choose F exactly to be squared, and then the weight, that is that one, to the power minus 1. And then G has to be chosen to be this way. Okay? So if you switch these quantities here, and then you simplify.
What's the definition of your W negative S?
Say again, what is that?
What's the definition?
The definition, yeah. This is a alpha that is given in terms, there are some constants, and then there is the McDonald function of order, I don't remember exactly, something like that, on delta plus R squared, and then times delta plus R squared to some power minus S. Maybe I'm cheating a bit, okay? Or S by 2 or something like that. Okay? So this is the weight. So again, coming to our expression, after simplifying with these choices, we have that, okay, let's call it right hand side of 2 is given by precisely what you got, what you get is, sorry, you will have this plus some integral representation of something positive. Okay, we will not give more details. And then for the left hand side, okay, one has to use that, I didn't say, but this operator is self-adjoint, and the key fact that has to be proven, of course, but I will not do it, and is the following. The axiom the action of this operator on this is precisely a constant okay, actually if you wish I will put better here. But this is a general identity. So this is the key point, that we know how to compute the action of this on these weights that are given in terms of McDonald function and things like that. And actually they appear naturally when you study the fundamental solutions of the operator. Okay? And this is giving us the constant that appears there. Okay? So when you mix these two facts, no? When you mix this, apply to the left-hand side of 2, and what we did for the right-hand side of 2, we went up with something that is some conclusion. We have that this equal equals this. I'm actually sorry, this is minus. Something that is positive. So as an immediate corollary, of course, we are then proving that this is positive. When you have this minus this is something positive. So as a corollary, you have the Hardy inequality, that is CD delta S, all these guys. And if you want something else, by using monotony properties of the McDonald's functions, okay, that says that they are increasing in the order, so you can end up with a more clean expression. Again, delta is a positive parameter, and of course you cannot do this tending to 0 because also the constant has this multiplying, so you are saying nothing. So actually, if we are here, this is sharp. So actually, this function, this weight, gives the quality. Okay. So this is our form for the Hardy type inequality for the Laguerre. Okay. Okay. So we work a lot, and then you will see that now, this is a matter of connecting with the Dunkl harmonic oscillator. Okay. So in the how much do I have? 10 minutes.
Oh, 15.
15. Okay. Then I will connect them with our. So then third part, Hardy inequality for Dunkl harmonic oscillator. Okay. Okay. So, well, Dunkl theory here they are experts like Professor Chu, Professor Lieb there, Gorbachev and Tikon. So this goes back to Dunkl. And actually, I will very rough, okay? And so these Dunkl operators have to do with analysis of attached to solve special functions and integral representation of reflection groups, okay? So I will just describe some basic ingredients. For that, I have to introduce which are called these reflections. So let's take a vector in Rd, and then I will define for x in Rd, I will define this reflection like taking this vector and then take the projection. So if I have a vector here, take the orthogonal plane. Take a vector x, project. Okay, this is the projection of x on u. That is actually this thing, and then reflect. Okay. So this is okay. So there is a key ingredient here that is called a reduced root system. Okay, R. So this is a finite subset of vectors such that for nu on R, what we have is this gives you back the reduced root system, and also for each element of the root system, the only multipliers are for each nu, so only multipliers are plus minus mu. So we can define the group generated by these reflections. Actually, also each root system can be expressed like two subsets that are divided by the hyperplane. And then, so if you take the group generated by this, we can define a function that we'll call a multiplicity function. Multiplicity. That is a function from the reduced root of system, and this is non-negative. Okay, and this is invariant under the action of G on I. Okay. So now with this ingredients I can define what is a Dunkl operator. That is the central ingredient in this theory. So the Dunkl that I will denote by, so take G between 1 and the dimension, is taking the derivative, and then plus, so you have to go summing on the R plus in the reduced root system. And then you have fxj minus fxj. And then I think here is the okay, I think I did it properly. So look, when kappa, well, this is supposed to be kappa, equals 0, this is nothing but the derivative. And actually, the most important feature of this operator is that they commute. That is something quite astonishing, right? So this is understand like the completely meaningful, yeah, that's okay. Generalization of the Euclidean derivative. Okay? So we have the derivatives, and then one can define the Dunkl Laplacian. Okay, the Dunkl Laplacian is defining this one. Okay? And there is a very rich theory analogous to the theory in the Euclidean case developed by people in this room concerning these operators. Okay, there are a notion of Fourier transform, translation, convolution. A lot of operators have been studied and so on, and they are very well understood. Okay, so I would like to yes, in the book by Dunkl and Chu, one can find a lot of information also in the previous works by Margit Rosler and many papers later on. Okay, so the Dunkl harmonic oscillator. The Dunkl harmonic oscillator is the operator defined like with the Dunkl Laplacian with minus plus x squared. Again, with kappa equals 0, well, of course, here when kappa equals 0, we recover the Euclidean Laplacian. When kappa equals 0, we recover the standard harmonic oscillator. Okay? So also this object has been studied quite a lot, and for instance, it is known that there are a system of eigenfunctions. I will call them kappa, b, and depending on some multi-index, and there are some eigenvalues. Well, all this mu is some multi-index, and these are the generalized Hermite functions. So once again, no, we are interested in taking the fractional powers of this object and take hard inequalities. And the idea will be just to reduce the situation to the previous situation of Laguerre operators. Okay, so this will be quite easy then. We have also the ingredients are there. So we have now that we can express the heat kernel like a sum of mu, and then we have a minus t lambda k du mu, and then we have some projections. Okay. Oops. Now we are in RV. Okay. Okay. Let me just. Okay. Okay, so the idea is now the following. Analogously as in the case of the Euclidean case, in the Euclidean case, you have an basis of spherical harmonics in the sphere. So one of the ideas that one can use often in Euclidean analysis to split into radial and spherical part, expand, and sometimes get advantage of the fact that the spherical harmonics are orthogonal system L2. Okay, so here in the Dunkl case, there's the same. Okay, there is you have in the sphere with the associated measure, you have a basis of H, what is called H spherical harmonics. Okay, so the idea now will be that one. We will span fractional harmonics. Okay, that I will denote like y. There is some running parameters. Okay, x prime. So one can express a function like the radial and angular part. So if we expand the function into each spherical harmonics, the key tool now is that one can express the heat kernel, the heat operator in the Dunkl harmonic oscillator setting in terms of Laguerre of the kernel of the heat Laguerre operator. Okay.
Well,
Yeah.
Can you please, corollary? I would like to see the corollary. Can you erase on the right?
Okay, sure. Yeah, I'm almost done. So, if we expand the function into each spherical harmonics and use a Hecke-Bochner, we prove a Hecke-Bochner identities. That relates the projections and the Laguerre convolution. So we can express like that, and then we are summing some parameters. Okay, I will not go into details. Okay, this is the radial part, and there are the corresponding coefficients and things like that. So I will not go. Okay, so remember that. So this is an identity that we prove, and then with that, what we do is to reduce this to this situation. So we have here the H spherical harmonics, and this is the heat kernel, heat operator for the Laguerre operator. But then what's going here? So consider the fractional operator, that is H, I will call H kappa S, the corresponding fractional operator. This is a sum in the corresponding eigenvalues, kappa, d, j, blah, 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 divided by the same, plus 1 minus s, and then projections. Okay, this is our fractional type, and then use this connection. I'm skipping several steps, of course. And then you bring up so this is the formula that we had, and then with that relationship, and we end up with something that is the sum m, j, r, m, and then now appears l, m, s. This is the fractional Laguerre. And then f, m, j, and now we are reaching the end, because if we want a hard inequality with for this, we will need to get a hard inequality with for this. But this, and so this is the final line. So apply. Inequality for Laguerre. And then we have theorem. So we are in L2 with RD. I didn't say if there is a weight attached to the Dunkl setting, and then we end up to this is bigger or equal, and the now after simplification there is some values here. Okay, there is alpha minus s here. This is made explicit, and then you have 0 times 0 infinity, and then x squared, and then square over s. There is the measure attached to the Dunkl setting. And of course, what's happening with this? Well, since this is an orthogonal base in L2, since I am taking this product in L2, this is killing this part, and then I'm just ended up with this operator. We apply the hard inequality for this operator, and then we end up with this. And then this is the end of the talk and the rest that I want to present. So thank you very much.
Thank you very much. Any questions?
Can you go beyond L2?
If I can?
Can you go beyond L2? Go to LP.
We haven't thought about that. We haven't. Actually, this method is very attached to L2. Yeah, I'll have to think about something else.
Right. So I have a question. So basically, in this corollary, you have two lines, and in your main theorem about Dunkl,
Yeah.
you basically take you have an analog of the second inequality.
Yeah, actually, first I skipped the first step. Of course, we first applied this, and actually there is a shift with the parameters appearing the same. You adjust, and actually you have to, to work a bit technically, but you can reach out this thing. But yeah, starting from here.
All right. All right. No questions. Well, if not, let's thank you.